Uh, so let's start our today's colloquium, and we are very happy to have Shantanu Desai from IIT Hyderabad, and he will talk about observational probes of cosmology. So welcome Shantanu, and I hand it over to you to start the talk now.
Okay, so thanks, Arpan, and thanks for the invitation. It's really a pleasure to give this talk, and oops, let me see. Okay, so
excuse me, can I see the speaker's face on the video?
Okay, is it okay if I show it at the end, because I think that consumes bandwidth, if that's okay? And
okay.
Okay, and usually here there are also power cuts, so I just want to be a little bit conservative. If that's okay, I'll show it at the end. Okay.
Sure.
Okay. So okay, so I actually cannot see the participant list now, so I don't know who's there, but just welcome everyone. And if there are like students and first year students from IIT Gandhinagar, also welcome to them. I think you'll have a great time at IIT Gandhinagar. So anyway, so first when I, let me just say something about the dilemma. First, when I got this invitation for a colloquium, right, I specifically asked whether I should give a colloquium or a seminar. So what is the difference between the two, okay? So my thesis advisor had told me colloquium consists of like, you talk about established facts in physics, whereas a seminar, you talk about your own specialized stuff which you're doing, which may or may not be true, okay? Another definition I heard from Bruce Allen, the director of AEI, is that once he invited me, he said only 10% of the talk should be about your own work. Okay, 90% should be based on, again, generally accepted facts and based on other people's works. Okay, so this talk is going to be neither of the two. I will have a sort of two tracks for most of the talk. I will sort of display some or show some of the established facts in the subject, and also make a few provocative remarks and present some contrarian viewpoints of some of the established ideas in physics. So this is a brief outline of my talk. I'll start with some rudiments of cosmology for the students. I'll mention the list of unsolved problems in cosmology requiring new physics. Then I will give a little bit of historical prelude on how cosmic acceleration was discovered using type 1a supernova. And then I will talk about galaxy clusters and then dark matter. And if time permits, I'll talk about inflation. So basically the talk consists of three disparate themes: dark energy, dark matter, and galaxy clusters, all possibly pointing to new physics. Okay, and again, I also looked at the list of previous speakers, very impressive list, and I think, but maybe this one will be the one closest to observations. Okay, so with that prelude, let me just dive in. Okay, so let me start with very basic about cosmology. So first thing you assume in cosmology is general relativity, or sorry, it's or a metric theory of gravity. So this is Einstein's equation on an abandoned train wagon somewhere in South America. Left-hand side is the geometry, right-hand side is the matter-energy tensor. So once you assume Einstein's equation, and then you assume the universe is homogeneous and isotropic, which we sort of know very well from observations, you can sort of show that I think the universe can be described by the Robertson-Walker metric on large scale. For any mathematical aficionados, you can look up Weinberg's 1972 textbook. I think Robertson-Walker metric satisfies lots of symmetry properties which have to do with killing vectors and all that. So the geometry, dynamics, and destiny of the universe is entirely determined by the matter-energy content of the universe. Okay, so what do we know about so how do we sort of, what are the constituents of the universe? So I think so the matter inventory of the universe is sort of parameterized by something called the omega parameter, which is given by, can you see my cursor or no?
Cursor, yes.
Okay, good. So omega is given by rho C, where Rho c is essentially 3h squared by 8 pi g. So basically, so this is actually the density parameter normalized to this critical density for the Einstein-de Sitter universe. So majority of the universe consists of dark energy. I'll explain what is dark energy later. About 25% to 27% consists of dark matter, and about 5% consists of baryons. The energy density of neutrinos is less than is greater than 0.1%, but it's not too large. And for photons, it is 0.01%. So with this constituent, we know that the universe is flat, but there's been a recent paper by Melchiori, Silk, and De Valentino, which sort of argues for a closed universe. So I think this is still a matter of debate. Okay, but just from this pie chart itself, we already have 3 problems. We don't understand this part, we don't understand this part, and we also don't understand this part. Okay, so I'll talk about this and this part later, but this part is called the baryogenesis problem, or why there's matter antimatter asymmetry. I think the consensus within the particle physics community, it is something to do with it's a beyond standard model of something to do with beyond standard model of particle physics. But I think if you work on, some people who work on gravity are also trying to make a model based on modification of GR. I think the buzzword for those who want to follow up is Chern-Simons gravity. Again, this was first proposed by Roman Chekiev in 2002. And again, if there's anyone who works on gravitational waves, people are trying to look for signatures of this with Lisa and so on and so forth. But that's all I will say about baryogenesis. Okay, so this lambda CDM, so we have a universe which consists of about 30% ordinary matter, 70% dark energy. So with this sort of matter energy budget, you can sort of work out the growth of density perturbations by solving, I think, Boltzmann's equation, and by just perturbing the Friedman-Robertson-Walker metric. And there are lots of Boltzmann codes which do this. So with so if the seed fluctuations we see in the cosmic microwave background, if you evolve them and if you study the growth of density perturbations in an expanding universe, you can sort of predict the formation of structures. You can predict the distribution of galaxies and clusters of galaxies. So for this reason, I think the 2019 Nobel Prize in Physics was awarded to Jim Peoples. Okay, so this is the 6-parameter lambda CDM model. So if you, with this 6-parameter lambda CDM model, you can very well predict the spectrum of density fluctuations. You can see this plot. So the x-axis is the wave number inverse of the scale, and the y-axis is the Fourier transform of the 2-point correlation function, which characterize whether a given region is over dense or under dense. And the dotted lines, the dotted points show the measurements. Oops, sorry, with error bars, and the solid curves show the theoretical prediction from 6-parameter lambda CDM. As you can see, that this model agrees very well with observation, which sort of tells us that this model is correct. Okay, so now I will come to sort of discovery of dark energy. So this was made using type 1a supernovae. Now we still don't know exactly what the basic physics of type 1a supernovae, but the most common accepted model is just the thermonuclear explosion of a white dwarf when it accretes matter from its neighboring companion. So these are its kinetic energy is about 10 to the 51 ergs. The light curves of type 1a supernova are powered by radioactive decays of nickel to cobalt to iron. So the first sort of insight which I think Mark Phillips had was that the width of the light curve is correlated with the peak luminosity. So if you look at this curve, you can see these are the supernova light curves with different peak magnitudes. Magnitude is just, for those of you who are not astronomers, is just a proxy for the brightness. So I guess smaller the magnitude, actually larger the magnitude when expressed in negative units, more brighter is the source. So as you go up here, the source becomes faint. So what he observed is that the peak magnitude is correlated with the width, okay, or the how wide the light curve is at a given point. And so this empirical observation can be translated can be used to sort of standardize type 1 supernova and make them standard candles. Okay, so this shows after applying essentially the Phillips correction. So with this, you can standardize type 1A supernova and you can make them standard candles. Okay, so once you have a standard candle, you can actually let's say a 40-watt. This is like equivalent to 40-watt light bulb. Okay, so if you measure its brightness at a given distance, if you measure brightness at various distances, you can figure out how far it is if you know the source. So something like this was also essentially done from the measured brightness. You can sort of estimate the distance, and if you have an independent measure of the distance from the redshift, you can actually calculate it for different cosmologies, and that's how people first discovered that the universe is accelerating. Now, to the best of my knowledge, we still don't have a first principle understanding of the physics of this Phillips relation, but this has been used by the cosmology community to standardize type 1A supernovae. Okay, so this I'll show you the Hubble diagram. So the x-axis is the redshift, y-axis is something called effective MB, which is just the brightness. So essentially what and this is proportional to the acceleration. So these are the data points, and these three curves show how MB varies as a function of the cosmological parameter. So omega m is the matter density, omega lambda is the energy density in dark energy. So as you can see, the data is more consistent with the solid line as compared to these two lines. Okay, and if you sort of compare the residuals, you can see that the data shows preference from these data points, which point to an accelerating universe, whereas these data show this is how a decelerating universe looks like. Okay, so basically what the supernova groups did is essentially extend the same measurements which Hubble did in the 1920s. So Hubble showed that the velocity of galaxies is proportional to the redshift, which established that the universe is expanding. What these groups tried to do is measure the first derivative of that curve. Okay, that means try to measure acceleration as a function of redshift. So that is what the y-axis implicitly tells you. Okay, so this showed that the universe was accelerating instead of decelerating. So this data is circa 2003. Same is true with I think later data 2010, and this evidence was soon confirmed by other cosmological probes, CMB, baryonic acoustic oscillation clusters, weak lensing, etc. And all of these point to concordance picture containing 70% dark energy, 25% dark matter, and about 5% baryons. Okay, so here you can see the updated data. Now, if you have a universe with cosmological constant, it actually decelerates in the past and it is accelerating now. Okay, and this is whereas I think for some exotic cosmologies you would always have a universe which is accelerating. Oops. And earlier what we thought was we live in a universe which is matter dominated. That means it is we should have seen a decelerating universe. So currently we live in a universe with omega lambda is equal to 0.75. Now the omega lambda is essentially flat, and omega matter decreases as a function of redshifts. At very early epochs, omega matter was greater than omega lambda. Now, one fun fact is that when the ancient dinosaurs roamed the earth, we lived in a matter-dominated universe. Okay, so it is not that recent. Sorry, it's not that old when the matter domination existed. Okay, so these two plots just show that if you derive confidence intervals for omega lambda and omega matter, 68%, 90%, 95%, they agree with CMB and other probes. Okay. Okay, so for this reason, I think the 2011 Nobel Prize in Physics was awarded. I think one half to Saul Perlmutter, the other half to Brian Schmidt and Adam Rees. These are two different groups which found evidence for accelerating universe from type 1A supernova. Same as the 2020 Nobel Prize, where I think the Nobel Prize was awarded to the PIs of two independent groups, which sort of pinned the case for a supermassive black hole at the galactic center. Okay, so now I come to my first sort of contrarian statement. Now, very recently, Subir Sarkar and his collaborators and students have made some very interesting observations. So when they looked at the supernova, they find that the 99% confidence interval, or the 3 sigma confidence intervals, is consistent with the non-accelerating universe. So that's one thing. And the evidence for acceleration is essentially marginal. So these are slides from a colloquium he gave at IIT Hyderabad about a year ago. Second interesting point which he makes is that you also see a dipole. The acceleration also shows a shows a dipole. That means it is positive in one hemisphere and negative in another, and sort of the symmetry axis is essentially close to the CMB dipole, as I understand it. So this is actually challenges sort of the standard picture. And he also, for those of you who want to know more about this, he also gave a colloquium recently at IUCA, for which you can find the slides on YouTube. And if you're looking for further speakers, then this is, you can ask him. Then he would be a good candidate where he can talk about all these details. Now, again, this is because this is such a controversial claim. Some people have also disputed it, and then Subir and his students have in turn counter disputed them, and so on and so forth. So this back and forth is still ongoing in the literature. Okay. Now you might ask, but aren't other probes consistent with an accelerating universe, which is what I myself showed in the, or myself I alluded to in my talk 2 or 3 slides earlier. Well, so one thing you should remember, that in any subject there's something called a confirmation bias. So this plot shows the speed of light as a function of year. Okay, and as you can see, as the error bars shrunk, okay, the values clustered around this. Okay, so there are 2 ways to interpret this. You can say the error bars become smaller and smaller, and this is the correct value. Another way to interpret is that when people got an answer which is not too different from the previous result, they didn't look for systematics and so forth. They sort of they were able to sleep peacefully at night. Whereas if they got a result which is different from the standard value, that could be the then they look very, very hard for systematic. For this reason, blind analysis is done in a lot of particle physics, and now it's also done in cosmology. But so question arises, does confirmation bias exist in cosmology? I think this was looked at in a paper by Croft and Daly, and I think the results are a little bit inconclusive. But if you look at the plots, right, so these are the measurements of cosmological constant as a function of year at small. At very earlier on, there were only upper limits, and then I think the first measurements came around here, and slowly all values clustered towards this. Okay, so I'll just leave it for you to think about this. Okay, so now there's another. So I talked about dark energy. Now here is another recent problem which has come up, which is called the Hubble tension and Hubble constant measurements. So this is a plot from a review about a year ago. So now Planck determines a value for the Hubble constant. Hubble constant is a rate of, if there are any students, rate of the expansion of the universe. If you measure the value of the Hubble constant from early universe observations, which is a CMB, you get a value of 67.4. If you measure it from Cepheids, you get a value of about 74, which is about a 4 sigma tension. By 4 sigma, I mean if you just take the difference between these 2 values and divide it by the errors added in quadrature, you get a value of 4.3 sigma. And again, there are a whole bunch of papers in literature of new physics, physics-based solutions to this, such as early dark energy and so on and so forth. Okay, and just to throw more just to spice it up a little, again, this Subir Sarkar and his student Mohammad Ramiz have also argued in a recent, again, a controversial paper or a provocative paper, that essentially there's no Hubble tension. The problem is just the problem in the redshifts by some of the supernova groups. So once you do the corrections, once you correct for the discrepancies in the redshift, you don't get any Hubble tension. Okay, I think Mohammad Ramiz has recently joined as a faculty member at TFR, so you can get more scoop on this by from him. But anyhow, so this is now the latest thing in cosmology, where you see at least one paper every 2 days in AstroPH, as well as in other parts of archive. Okay. Okay, so now let's assume that that the universe is accelerating. What could be what are the most likely explanations for this. Okay, so let's try to understand the main difference between GR and Newtonian gravity. In GR, pressure gravitates, whereas in Newtonian gravity, pressure counteracts gravity. So if you take an ordinary star like sun or galaxy clusters, one reason it doesn't collapse to infinite density is because it is held against collapsing by essentially pressure. So in Newtonian objects, pressure sort of balances gravity, whereas what happens in GR is pressure gravitates. Okay, that means as the gravity gets stronger and stronger, at some point pressure, instead of trying to play tug of war against gravity, it switches sides, and it believes in the principle, if you cannot beat them, join them, and essentially it's also gravitate. That's one very heuristic way to understand why you essentially have a black hole. So same thing happens in cosmology. So you replace the energy density rho by rho plus 3p, and then the acceleration is you can write down in the acceleration is given by this expression. So when the universe is accelerating, this quantity must be less than 0, rho plus 3p. Now, this is not actually predicted by GR, because if you take most ordinary matter, its rho is either positive or 0. Okay, for this, for my laptop, rho is rho is 0, and so on and so forth. For energy, for radiation, rho is equal to 1/3, and so on and so forth. So obviously we need some extra component of matter energy density, which will sort of act in such a way that rho plus 3p is less than 0. So this unknown substance is called dark energy. This term was coined by Mike Turner around 1998, but I think this word is a little bit of a misnomer. I think dark pressure or smooth tension would have been more appropriate. Okay, so what's the simplest example of dark energy is just a cosmological constant. It's just the energy density of quantum vacuum. It has the equation state P is equal to -1 by rho. Now there is actually one problem which I won't go into the detail because I'm not an expert, but I think your local hosts can tell you much more about it. So the observed value of cosmological constant, assuming dark energy is because of that, is 10 to the -12. EV to the power 4, whereas the theoretical prediction is 10 to the 76 GeV to the power 4. So that means the theoretical prediction is 10 to the 120 observed. So I think Frank Wilczek has called this as a most embarrassing example of order of magnitude calculation gone wrong. Okay, so for this reason, people have also proposed other alternatives to other solutions for dark energy, because it's very hard to come up with a mechanism which will cancel up to 120 decimal digits and yet give you a value of 0.7. Okay, so the two sort of most widely used modification. One is just addition of exotic fields or matter, or you modify GR, or you argue that the universe is not homogeneous. Okay, and there are more than 10,000 papers on different explanations, models of accelerating universe. I think Mike Turner has called this the most profound mystery in all of science. Now, usually observers parameterize dark energy by equation of state W is equal to P by rho. Okay. Okay, so now comes my sort of first provocative statement. So there's actually lots of elephants in the room in the problem. Now, when a lot of cosmologists have worked on modified theories of gravity, such as F of R, Galilean theories, Hondesky's theories, many more examples, and and one of the main sales pitch for next generation dark energy experiments such as LSST Euclid is to look for signatures of these modified theories of gravity which emulate cosmic acceleration. However, if you talk about these modified theories of gravity to people who do strong field gravity as well as strong field gravity or quantum gravity, they'll literally frown at you. They'll literally throw up. Okay, they don't like these theories, and if you sort of press them, they say that these theories are not stable. They don't predict stable neutron stars. In fact, people like Damour and others have not published even a single paper on this modified theories of gravity. But cosmology community has built a straw man, publishing paper after paper on these theories, and they look for observational signatures of these theories in modern experiments. Okay. So second thing is, I think what the cosmological constant problem, which I mentioned 2 slides earlier, I think it is this is also complete hype by, according to Eugenio Bianchi and Carlo Rovelli, and they have argued in this very provocative paper that the cosmological constant problem is as interesting or as uninteresting as why electron mass is 0.5 MeV. Okay, so it's just a hype created. Okay? So again, I won't take any stand on the second paper, but this is just to present a contrarian viewpoint. Okay, so I think I want to change track, but are there really quick questions on the first part?
If anyone have questions, you can ask now.
Very quick questions.
Okay, then maybe go ahead.
Okay, fine. Okay, so
Hi,
now yeah,
this is Sriram here.
Yeah.
Shantanu, why are you saying that there is a lot of effort in examining modified theories, and also one hopes that these gravitational wave observations will lead to strong constraints as well, right?
But so that's a good point. So these modified the modified theories of gravity, which the people in the gravitational wave community are pursuing, in those theories, GR is modified in the strong field regime. Here in these theories, GR is modified in the weak field regime or at long distances. Okay, so it's modified in the infrared. Okay.
So your concern is about theories which try to explain late time acceleration rather than you don't have any issues early universe.
Yeah. And I mean, this is not my point of view. This is, in fact, this is something which Sergei Kopekin told me. I haven't had this discussion with Damour, who is again one of the doyens of strong field gravity, but he has not published even a single paper on this. And I think even people who work on quantum gravity or string theory, I think these kinds of theories makes them cringe. Now, obviously, that doesn't mean these theories are wrong. Okay, I'm just, as I said, I want to be provocative and this thing. But yeah, the modified theories of gravity, which people in the gravitational wave community are pursuing, GR is modified in the strong field regime. Although to correct myself, I think Shubhendra Mohanty, Sukanta Bose have also looked for signatures of FFR gravity in gravitational wave observation recently. So I think the distinction is not that sort of black and white, but mostly that's essentially the philosophy.
Also, one hopes things like Euclid will constrain using the growth factor and
and one more So one more thing, right now we don't have any evidence for modified theories of gravity just from growth of structure. Okay, but the question is, if you just have growth of structure, then is that just an evidence for just abandoning Einstein's gravity? And actually, this comment was also motivated by one seminar given by a very famous, I think, cosmologist whose names I won't take, who was giving a book showcase. And then I think Gyadwali said all these theories are nonsense. I think neutron stars will not be stable. Okay. So anyhow, I'll leave it at that. Okay.
Thank you.
Okay. So anyway, this is my first provocative remark. There's more to come. Okay. But let's go to observations.
Can I have a short question?
Sure.
And that the decelerating phase of the universe, how strong is observational evidence? Direct.
The work by Subir Sarkar, you mean?
No, so supernova type 1a.
Okay. So
directly observes accelerating expansion, but decelerating phase, how strong the observation?
Oh, okay.
How direct?
Yeah. So I don't know how many statistical significance, but one thing you can do, right? You can actually plot with cosmic chronometers. You can plot HSV versus Z, and there you can find out the turning point. Okay, so it's not data not completely consistent with acceleration, but I think if you're asking for just statistical significance, it is weak because we don't have too many measurements at high redshift. I think the turnover happens around redshift of 0.3 or 0.4. I think Bharat Ratra has written many papers on this around 2011, 2012. I think one of my BTech students also did this, but I forget the exact the redshift. But anyway, to answer your statistical significance question, I don't think it is very strong, but I don't know the exact number. Okay, can I go ahead?
Sure.
Okay, so Okay, so now I'll come to more observations. So galaxy clusters are the most massive gravitationally collapsed objects with masses greater than 10 to the 14 solar masses. I think they consist of 85% dark matter, 2% galaxies, about 13% plasma baryons. So the typical size is about 1 to 10 megaparsec. They're seen at all wavelengths from radio to X-rays. They have not been seen in gamma rays. There are one or two claims. They're not very convincing. So in last 2 or 3 decades, a large number of galaxy clusters have been located in optical X-ray microwave for the past 2 decades. And again, galaxy clusters are also the flagship objects for next generation surveys. And again, galaxy clusters are sort of the excellent probes. They're like bread and butter probes of dark energy because they're sensitive to both the growth of structure, growth of density perturbations. So if you have more dark energy, growth of density perturbation is suppressed, and they're also sensitive to the volume, okay, and neutrino mass, galaxy evolution. So I've worked on a few of these things, but I'm not going to present these results because there are, I think, there are many other experts who can discuss in more detail, okay. So so now here is something I'll share a sort of a story. So I think when the LIGO detection happened, all of you, I read the LIGO GW 1509114 PRL detection paper, and here is what it says. So one of the key I think in the very first PRL paper, I think they just had a statement on they obtained a limit on the mass of the graviton. So I'll just read this aloud. Finally, assuming a modified dispersion relation for gravitational waves, our observations constrain the Compton wavelength of the graviton to be greater than 10 to the 13 kilometers, which could be interpreted as a bound on the graviton mass of 10 to the minus 22 eV per c square. And the way they have obtained this is just basically assuming E square is equal to, just assuming that the speed of the graviton gets modified just from the special relativity dispersion relation, and then the phase also changes. So that's how they get the mass of the graviton from the black hole observation. I think from neutron star observation, you can use the fact that they're close to each other. So this improves on the solar system and binary pulsar bounds by a factor of few and 1,000. Now, the next statement essentially literally made me jump from my chair. I'll tell you why. But does not improve on the model-dependent bounds obtained from dynamics of clusters and weak lensing observations. Okay, and I looked at this reference. So reference 100 is from 1974. Reference 101 is from 2002. So I at that time I've been working on galaxy clusters for about 8 years. I have not seen even no one actually mentioned anything about galaxy clusters and graviton mass. Okay. And same with weak lensing. There are lots of people working on weak lensing, but apart from this paper, no one has sort of used weak lensing to constrain the graviton mass. And just as an aside, actually, the LIGO PRL detection paper cites there's a typo in the reference. Okay, this should have been the reference, but they've cited a different S. Chaudhary. But anyhow, so this really made me jump from my chair. I thought actually we need to do something. Okay, the last word on graviton mass using galaxy clusters cannot be from 1974. Okay, so then what I did was I searched various literature, checked what kind of objects, what kind of clusters are best suited for limit on graviton mass, and so the idea I used is very, very simple. Actually, I haven't gone into detail on how this limit was obtained, but you can ask me later. I think I'm already running behind. So, okay. So basically, what I did was you make the simplest assumption, assume that the whole galaxy cluster is a point mass and obeys Yukawa potential, and then you ask, given the error bars, how much are the difference compared to NFW model, which we know fits the galaxy cluster data well. From there, you can get a limit just by plotting, by comparing the deviation as a function of the distance from the center of the clusters and calculating the sort of the chi-square differences between the two, and you get a limit of about 10 to the minus 29 eV, which is great, or it corresponds to Compton wavelength of 9.1, 10 to the 19 kilometer. And again, there are actually different ways of setting a limit on graviton mass. And one way is you assume in the non-relativistic limit, this graviton mass, a non-zero graviton mass the potential is a sort of a Yukawa potential. So using that same idea, I think so our work was followed up by work done by a group at Delhi universities, which obtained a limit of 10 to the minus 30. So we did some further work. So this work was done with a summer intern, and I think the best limit we obtained from stacking red matter clusters is about 1.2 and 10 times 10 to the minus 30 eV. Now, honestly, if you ask me, I don't know what is special about graviton mass, but people again who work on gravitational waves, they are very much interested in the limits on graviton mass. I think I've seen papers by Cliff Phil as early as 97 on how well LIGO can constrain graviton mass, how well LISA can constrain graviton mass. So this limit, but cosmologists are not really interested in this. So there's, again, this comes back to what I told Sriram. There's a little bit of a disconnect between the cosmology community and gravitational waves community, but you can turn it around into an opportunity, and you can try to constrain or work on theories which you can constrain with cosmological observations, but in which no one else is interested in. Okay, so that's just a sociological comment. Anyway, so I think the best limit which we get is around 10 to the minus 30 eV, but the lensing limit is the most stringent one of 10 to the minus 31 eV. Okay, so now I will change tracks. I will talk about one very interesting detection method for detecting galaxy clusters, is something called the Sunyaev-Zel'dovich Effect. Okay, so if there are students, probably in your modern physics class, you must have heard about ordinary Compton scattering, where a photon gives its energy to an electron. Now in astrophysics, we have the inverse situation called inverse Compton scattering, where I think, and if you have electrons whose energy is greater than the photons, and the electron transfers its energy to the photon. So this is called inverse Compton scattering. I think this was first worked out by Dirac, and I still don't know when it was first discovered in the lab. But anyhow, so this is sort of ubiquitous in astrophysics. If you have a general sort of plasma, then you can have both Compton scattering, inverse Compton scattering, and then the evolution of the number density is given by a Compton-Eats equation. In the regime, if you have a galaxy cluster along the line of sight to the CMB spectrum is black, is a perfect black body. And if you have a galaxy cluster along the line of sight, because of the inverse Compton scattering, the CMB spectrum gets distorted, and the distortion of the spectrum is quantified by something called the Y parameter, which is essentially the integrated Compton ionization along the line of sight. So in this plot, so here's the distortion if you have a cluster. Your Y is equal to 0.15, but typically in the real situation, the value of Y is very, very small, is 10 to the minus 3. Okay, so Sunyaev is still working on various other kinds of distortions, and his sort of right hand in all of these collaborations is Rishi Khatri, who's in TIFR. So if you want to know more about other kinds of very, very interesting distortions which you can detect with next generation CMB experiments, you can sort of invite him for a talk. Okay, so here we'll just talk about so galaxy clusters, the Sunyaev-Zel'dovich effect because of galaxy clusters. Now, one reason why this is such an important probe is because all other astrophysical emission processes, essentially the flux goes as 1 over r square, whereas because this is the surface, this is just a distortion of the spectrum. The intensity is not sort of redshift dependent. It's just dependent on the amount of hot gas which exists in galaxy clusters. So because of this, we can detect galaxy clusters up to a very, very high redshift. Okay, that's why this has become such a cool probe. Okay, so now I'll just show you some pictures. One experiment for which I worked on for many years. This is the South Pole Telescope, 10-meter telescope located at the South Pole. One reason you go to the South Pole is because I think the air is very, very dry there. And it measures CMB and anisotropies up to very, very small scales, and it 0.02 degrees, and it conducted the 2,500 square degree galaxy cluster survey between 2008 and 2011. Okay, so I'll show you some pictures. So the left side shows a microwave image, and Sunyaev-Zel'dovich effect obviously seen in the microwave, just in CMB. This shows I think the SZ increment. By the Sunyaev-Zel'dovich effect nowadays is just called SZ. Here shows an optical image of this. But one disadvantage of SZ effect is you cannot measure you cannot directly get the redshifts. You can only you can only get the intensity. To get the redshift, you need to do optical follow-up observations. So this is again another redshift cluster, and I've observed for about 1 month some of these redshift clusters, cumulative nights of about 1 month. This is again a much a higher redshift event. This is this optical this image is from Spitzer. You can see the star formation here. Okay, so this sort of exemplifies what I just said a few slides ago. So the x-axis shows the redshift, y-axis shows the M500, and these are the clusters detected by the SPT. The dotted is from the 2,500 square degrees survey. There are further follow-up surveys. There's also another experiment, ACT, where and so basically the main point is, as you can see, we have seen the massive galaxy clusters up to very, very high redshift. Okay, this otherwise wouldn't have been possible with X-rays or other kinds of surveys. Okay, so obviously with SPT you have also detected you can there's lots of papers have come out constraining the cosmological parameter, constraining, I think, modified theories of gravity. I won't go into that. Something which a student and I have been exploring is to look for constraints on variation of fine structure constant. The idea is very, very simple. For many SPT clusters, you have X-ray follow-up observation. So the X-ray, what is called a YX parameter, which is the mass of the gas times temperature, and its SZ counterpart, its ratio scales as the fine structure constant cube. Okay, so if you just make a model for the variation of the fine structure constant, delta alpha by alpha, if it's given by this, you can get something by this. You can look for such a variation, as you can see from this plot. So this shows a ratio of the SZ flux to the actually SZ comptonization to the X-ray comptonization. The ratio is essentially flat as a function of redshift. From there, you can set, so as you can see, there's no variation in alpha. And from here, you can set limits on on this gamma, which is consistent with 0. Okay, so now I think the next big player in the game is the E-Rosetta X-ray satellite, which was launched in July 2019. It should discover about 100,000 clusters. I think they've already given seminars where lots of new clusters have been discovered. I think their first data release is going to come out in I think next month. Okay. Okay. So now I gave you a prelude to X-ray surveys. The big revolution which is happening in this field is the era of optical surveys. So again, the first survey is the CFA redshift survey, which detected 2,500 galaxies. The big sort of game changer is sort of SDSS. Again, it started in 2000. I think SDSS ran in various phases. As of 2010, it had detected 1 million galaxies. Currently, we are in SDSS 5. So these are some of the big surveys. The name of the game in surveys is you build giant imagers with state-of-the-art technologies, just mount them on 4-meter class or 8-meter class telescope and survey contiguous regions of the sky. Okay, so these are some of the surveys. I'll spend a few time talk of something on about a dark energy survey, for which I think I have a builder status since 2010. Builder status implies if you do 2 or 3 years of infrastructure work, you get builder status. So and again, then the sort of, if there are any particle physicists, the LHC of optical astronomy is going to be the LSST, the 8-meter telescope. I think here IUCA is, and also IAA are involved in this. Okay, so this, I'll say something about a dark energy survey. So it's a survey project using 4 complementary techniques to measure again dark energy equation of state using all the 4 techniques which were used to obtain evidence for cosmic acceleration. It also built a 3-degree camera. This was built at Fermilab. And one of the things I worked on a lot on DS is the data management system. That means just to analyze terabytes worth of data from these optical telescopes is sort of a computational challenge, and it's going to get even worse for next generation surveys, such as LSST. So I'll show you some pictures of clusters. So again, this is a 0.35 galaxy cluster, redshift cluster. Again, another picture of that. This is another redshift of 0.4 clusters. And this is a cosmological, this is a random plot from cosmological constraint from year 1 DS data. I think the key plot is here. I think everything is sort of consistent with the best fit value W of close to -1. Again, someone can give a whole talk on just this slide or similar slide from other surveys. Now, if you looked at the abstract, right, I said I'll talk about a few technical challenges. So here I'll mention just one. So all in cosmology, basically you have to optimize a parameter space which consists of 7, 8, 10 many free parameters along with lots of nuisance parameters. So sort of the workhorse tool for that is something called MCMC, Markov chain Monte Carlo. Now, one thing which my CS colleague Srijit has been pushing for is something called variational inference, which is an alternative to MCMC. It sort of computes, it sort of approximates the posterior using sort of analytical function, and the best analytic function is found from the KL divergence. So this is a slide made by an MTech student in computer science department working with Srijit, Professor Srijit and myself. And for more details, you can look up this archive article. So there's the first technical slide. Okay, so another thing I've been working on. So one other problem with these optical surveys, right? They contain a lot of junk from cosmic rays, satellite trails. So that is going to get even worse when I think when Elon Musk's satellites are up. So here is an image. Here's a DCAM image. Here you can see the different cosmic rays. So what we have done, a sort of a brute force algorithm where we combine multiple images and then compare with the original image to remove the cosmic rays. And this is a clean image after you remove the cosmic rays. Again, here you can see a satellite trail, and this is application of the same algorithm. Okay, so that's it about DS, SPT, and surveys. Any quick questions before I get to the last part of my talk?
If you have any questions, you can ask. Okay, maybe you can go ahead, actually.
Okay, fine. Okay, so now I come to the last problem, the dark matter problem. Okay, I think all of you sort of know. In fact, I think even someone who doesn't work in astrophysics knows that if you look at the curve like this, you see flat rotation curve, whereas naively what we expect from observations is that we would expect to see a rotation curve which would fall off. So the hypothesized solution is that the visible galaxies are embedded in much larger halos and structures of dark matter. Now, there are lots of dark matter candidates. Just last week, I think there was a conference organized at ICTS on different models for dark matter. But the most widely studied one is something called WIMP. So why is that? So let's say if you have a thermal relic with annihilation cross-section just of the same magnitude as electroweak couplings, that has just the right properties. That means it has the right relic abundance, and it also behaves like a cold dark matter. That means it decouples when it is moving at non-relativistic velocity. So this is exemplified by this curve. This is from a paper by Steigman, Dasgupta, John Beacom. This is Basu Dasgupta from TIFR. As you can see, so early on, if you have a relic particle with electroweak coupling, it is in thermal equilibrium. But when its the annihilation cross-section falls below the expansion rate, then the relic abundance freezes, and you get something like this. So if it has a weak scale coupling, it has just the right properties to be a dark matter candidate. So this again, this is an old idea. It was worked out in 60s and 70s by Zel'dovich, Weinberg, also by Ram Kaushik, Lee, Ben Lee, Gary Steigman, Jim Gunn, McLennan, and many others. So this idea is essentially known as the WIMP miracle. Okay. Now, there are a whole bunch of underground experiments which are looking for this, looking for these signals of WIMP in direct detection experiments. So this is the y-axis is the WIMP nucleon cross section, x-axis is the mass. None of them have seen a WIMP, so these curves are sort of exclusion curves. So all cross sections above these are ruled out, except for one, Dama. which I'll say something about, Dama Libra. So what is why do Dama claim they've seen this? So so essentially, if you have a dark matter halo, and if you have Earth moving around the sun, and if the sun basically follows the same trajectory around the galactic center as the dark matter, then based on what we know about the motions of dark matter, in sort of June, we would get a higher flux of WIMPs, and in December, we would get a lower flux of WIMPs. So this was worked out in the 80s, and Dama experiment actually sees exactly such a signature. So this dotted lines are sort of the residuals as a function of time in an energy range of 2 to 6 keV. This is where we would expect to see the WIMP signal, and that is consistent. The annual modulation phase, that is peak around June, amplitude 7%, it sort of agrees with the signal predicted in 80s. So what's the problem? The main problem is no other similar experiment has seen such a signal. Okay, so again, lots of particle physics theories have been concocted to sort of explain this discrepancy. One of the things I did for my thesis is to set a limit on the WIMP proton axial vector or spin-dependent cross-section, which you can check from spin-dependent, which you can search from WIMP annihilations in the sun. And that rules out that the Dama signal to be due to WIMP proton couplings. Okay, but again, this is lots of particle physics theories have been concocted. It's still an open question as to whether Dama collaboration has really detected dark matter or not. Most people don't believe it. A few people are taking it seriously. One problem is that the Dama collaboration refuses to release their data. Okay, whatever analysis people have done are essentially obtained by digitizing the data. Okay. The one thing which I've recently done with another summer intern, Aditi Krishak, and one of our own BTechs is to do a Bayesian analysis of Dama data, as well as other experiments which use sodium iodide as a target. And I think we made some forecast. And I think within 5 years' time, if there's a real signal, you can easily tell for experiments with a base factor of 40. Okay, for more details, you can look up these works. Okay. So now I come to another elephant in the room about the WIMP paradigm. Again, I said I'll be provocative. You can judge how provocative I've been. Okay. Now, I should mention this slide is my personal opinion. I think 99% of the physics or astronomy or particle physics community will disagree with me. But anyhow, so at the end of the day, the WIMP miracle is only a numerical coincidence. We don't have even a single shred of evidence from any astrophysical observation that the cold dark matter has electrovariant couplings with matter. The only sort of quasi evidence is the numerical coincidence, which is that if you have a relic particle which is stable and which has electrovariant coupling, it provides the right properties to be a dark matter candidate. But just the ordinary cross sections have already been ruled out. Okay. Now I'll give you another example of another numerical coincidence which has sort of been ignored by everyone except J.D. Bjorken with BJ. So I'll just quote from his paper. This is what I call the Zel'dovich relation. In natural units, the cube of the QCD scale is of the order of the Hubble scale. It was noticed by Zel'dovich in 1967 and has occasionally been rediscovered in the interim. I encounter it often in my speculative excursions into trying to understand the dark energy problem, and I now take it seriously. I find this as a minority viewpoint. So anyhow, here you have a whole cottage industry around a numerical coincidence. Here, nobody takes this numerical coincidence seriously except for BJ. Okay, so you can decide among yourself with you can just draw your own conclusions from it. Okay, so second concern is, have the goalposts moved? Okay, so this is a plot by David Merritt, which shows the cross section as a function of WIMP mass as circa 2002. Here you can see the limits from the experiments at that time, and you can the sort of the pinkish curve is the predictions from theoretical models at that time. Now, if you make the same plot with the same scale circa 2015, you can see that all the theoretical models have become smaller and smaller. So what this means is that the WIMP paradigm can never be falsified, can never be ruled out. Even if all the experiments don't detect it, particle physicists are always clever and come up with models which evade all these bounds. Okay, so that's one concern. Now, so that was about a WIMP paradigm. So some concerns about the dark matter paradigm itself. Okay. Okay, so now if you actually look at the rotation curves, okay, where you see that the theoretical rotation curve falls off, but the observed rotation becomes flat. You might think that you can then ask the question, at what point do we need dark matter? So the way to quantify is to calculate the dynamical mass over the observed mass or over the visible mass, or you calculate the total velocity divided by the baryonic velocity. So this is that plot. There's nothing very spectacular about this. But one thing which I think Milgrom notices that if you plot the mass discrepancy as a function of acceleration, I think this one of them is the baryonic acceleration, one is the total acceleration. You find that the need for dark matter kicks in below a fixed acceleration scale for all galaxies 10 to the minus 8 meter per second squares. Okay, so this is called a mass acceleration discrepancy relation, and this cannot be easily explained. Well, it cannot be easy. I was going to say this cannot be easily explained with lambda CDM. In fact, I don't think I've seen even a single paper. I've seen only one paper which tries to explain this within lambda CDM, but here this is an observed empirical fact. Okay. Second, so this is again another plot, same plot made by Stacy McGough over a wider acceleration scale. So you can see that the mass discrepancy kicks in at below 10 to the minus 10 meter per second square. Then I think another observation made by is that something called a baryonic Tully-Fisher relation. So if you look at rotation curves, I think from y-axis you can deduce an asymptotic value for the total velocity. If you plot that versus the baryonic mass, okay, you will see a very, very tight correlation. Now, if you naively think about it, so dark matter constitutes 90%. 90% of galaxies are made up of dark matter. So baryons are subdominant. So there shouldn't be any strong correlation. But yet, what people observed is very tight empirical correlation between baryonic mass and asymptotic velocities. So this is called the baryonic Tully-Fisher relation. And it's on the log scale, it's a linear relation. I think you can, the slope alpha is consistent with 4, beta is equal to G over A, and A is equal to V4 by GMP. Then another such observation made by again Stacy McGough is that if you plot the total acceleration against the baryonic acceleration, it shows a very pristine deterministic relationship with total baryonic acceleration with very, very negligible scatter. You can see it from this plot. So the x-axis is the baryonic acceleration, log of that. Y-axis is the total acceleration. There's a very nice pristine relation given by this. Okay? Again, this cannot be easily explained in lambda CDM. Now, one again sociological fact. Again, this was pointed out by David Merritt, not by me. He actually surveyed a large number of cosmology textbooks. Okay, and did a survey to see do how many of these textbooks mention these 3 points: the failure of laboratory experiments to detect dark matter, is the existence of a universal acceleration scale discussed, is the mass discrepancy acceleration discussed. Almost all the textbooks you'll find no. This includes books by, I think, Nobel laureate Steve Weinberg. It also includes Jayan's book, which has a completely contrarian approach to cosmology, but even that book does not mention these empirical relations. Okay, so somehow it's as if, I think David Merritt's point is that the cosmology community doesn't want students to know about these observed empirical facts. Okay, I don't know why, but anyhow. Okay, so anyhow, so based on these observations, Milgrom made the following ansatz, that if you just posit that for acceleration less than A0, if Newton's law gets modified as square root of Gn times A0, then one can trivially get this relation with just one line of algebra. You just write G as V square over R, and from there you can trivially get A0 times Gm. And to get a smooth transition between the two regimes, I think Milgrom then proposed a mathematical relation between the two accelerations. Mu is some interpolating function. I think for one of the interpolating functions, you trivially get a radial acceleration relation. So this modification is called modified Newtonian dynamics. It works remarkably well for galaxies. However, its honeymoon ends when you apply this relationship to clusters and also when you try to construct relativistic theories. So MOND does not work well for galaxy clusters. Again, this is known for a long time. So whatever you do, you always get a dynamical mass which is greater than the baryonic mass. And recently with a BTech student also, I looked at this. Second problem, now the jury is still out on all those empirical observations which I showed in the previous 2 or 3 slides work well on galaxy clusters. One is the radial acceleration relation. I think earlier this year, there was a paper by Tian which says that RAR works for galaxy clusters. But another paper by Shan Del Popolo, as well as some work done with BTechs at IIT Hyderabad, showed that it does not. I mean, by it does not, I mean that the scatter is very, very large. Okay. Then there was a paper, I think, by Ravi Sheth, who showed that I think baryonic Faber-Jackson works for galaxy clusters. Another observation which was found, I think, a decade ago is that galaxies have a constant dark matter halo surface density. Again, that can be trivially determined, I think, comes out from MOND. Or from Milgrom's modification. Again, I think there was a study of this in 2014 by Shen using the Rosat sample, and he showed that galaxy clusters, they don't have a constant halo surface density. But recent work done by my PhD student shows that it does for a sample of 12 clusters from the Chandra X-ray sample. So that is about these empirical observations for clusters. Now, again, there was a lot of work many years on sort of trying to construct relativistic theories of MOND. I think Bekenstein succeeded in 2004. But one thing which we have done, one thing which we showed is that most relativistic theories of MOND are ruled out by the simultaneous gravitational wave detection of GW 170817 and GRB 170817. So the idea is that we use the fact that the line of sight Shapiro delay is same for photons and gravitational waves. So what do you mean by Shapiro delay? So normally, I think in all popular science books, and you must have heard that the gravitational waves propagate at the speed of light. Well, I think it's slightly more nuanced. I think I think the universe is not empty between GW 170817 and us. There's matter, and I think Erwin Shapiro showed that the speed of light depends is a function of gravitational potential along the line of sight. Same is true for gravitational waves. So gravitational waves also gravitate, or they get slowed down by gravity. If these relativistic MOND theories were correct, then gravitational waves would have arrived much earlier because they do not feel the Shapiro delay of ordinary matter, whereas photons would have. Just from the simple observation that the photons, that the gamma rays and gravitational waves arrived within a second, you can rule out most relativistic theories of MOND, okay, including Tevez. Okay. So again, so even though the MOND is a nice paradigm, I think it runs into trouble with clusters and so on and so forth. So then you might ask, what is the explanation for those empirical correlations which I just showed? I think the answer is we don't know yet. Many people have been pushing for self-interacting dark matter. Luc Blanchet has been proposing, I think, dipole dark matter. Justin Curry has been proposing, I think, superfluid dark matter. I think, whereas if you ask someone who works on lambda CDM, they'll tell you that all these things can be explained using feedback. But again, to me, it's not obvious because feedback is a stochastic dissipative process. It's not obvious how feedback will magically cancel and give all these relations. So recently we had a seminar by Manoj Kaplingar from UC Irvine, who says all this can be explained using a self-interacting dark matter with a cross-section which decreases as a function of velocity. Okay, so the jury is still out on that one. Okay, so now I am out of time, so I can skip. I just had 2 slides upon inflation. I can just skip it and take questions, or I can just say something about inflation. I think you people can decide. The host can decide. I think I'm already past the time.
Then you can probably skip, and if there's some question they will ask.
Sure, okay. So then I will just stop. Okay, so again, I'll just summarize this. I won't repeat this. Thank you for your time and attention. Hope this talk, if there are students, hope this talk inspires you to solve this problem, and also critically analyze some of the established facts in cosmology. Okay, thank you.